Well, hello and welcome back to another episode. It's great to see you all. I hope you're doing well. So today we're continuing with our series looking at writing a ray tracer in C++ using as far as possible only the standard libraries, and I'm also using the SDL2 library simply so that we can display results in a window. The episode today we're going to focus on boxes and cubes and how we can go about actually implementing boxes and cubes. So far we've looked at kind of the classical ray tracing shapes. We've looked at planes and spheres. Those are the classical ones used by just about every ray tracing tutorial out there. We've also looked at cylinders and cones, which makes things a little bit more interesting, and we've talked about how we can define all our objects in their own local coordinate system that makes it much easier to do that. But all of those shapes so far, they've all been defined by one specific implicit equation. A box is a little bit different, or a cube is a little bit different. Now, I suppose maybe you could do something with Fourier series or something like that to make a box out of spheres, but that would be tremendously complicated and would be very, very slow. Luckily, it turns out there's a much easier way to do it. The most obvious, of course, would be simply 6 planes, but it turns out we can optimize and do better than that. So that's what we're going to talk about today. But just before we jump into that, I want to say, as I always do, that if you like this video, please do remember to hit that like button. It really does help with the YouTube algorithm. And if you haven't subscribed to my channel already, then please consider doing so. I do try to post videos fairly regularly. I'm working through this ray tracing in C++ series, many great videos and a lot of what I hope will be interesting content planned. So if you subscribe, you don't need to worry about missing anything. Thank you very much. Anyway, without much further ado, let's jump into it and let's have a look at how we can implement boxes in our ray tracer. Okay, let's go. Okay, so here we are. We're now on episode 12, and as I just said in the introduction, we're going to talk about boxes or cubes, but of course we can scale them to any shape that we want. So just to recap about line-plane intersections. So we talked about this before, and we talked about how we have a plane represented in vector form. You can hear that some point on the surface of the plane is given by the sum of an origin point, P0, and then a vector from P0 to P1 multiplied by some scalar quantity u, plus a vector from P0 to P2 multiplied by some scalar quantity v. Okay, that's pretty straightforward. And we can then represent a line. In our case, this is our ray, of course, cast from the camera or wherever in the scene. It's also represented with some point x is equal to some vector a plus a scalar quantity t multiplied by a vector k. And of course here, k defines the direction of the line and a is a point on the line. Okay, and therefore, of course, we can calculate line-plane intersections simply by making these two equal to each other. So we have the vector a plus tk is equal to p0 plus p0 1u plus p0 2v, and we can rearrange that to give that the vector a is equal to this vector here minus k, p0 1 and p0 2 multiplied by the scalar quantities. And then, of course, we can rearrange that quite easily to give our value for t in terms of what we know. And then we can solve for the other unknowns u and v as we see fit. Okay, now for a horizontal plane at the origin, okay, we can define that P0, our origin point, for the plane, we can simply define as the global origin, 0, 0, 0. Okay, P0, 1 can simply be a vector pointing in the positive x direction, so it's just 1, 0, 0, and then P0, 2 is just a vector in the positive y direction, 0, 1, 0. And therefore we end up with this, that a is equal to 0, 0, 0 plus u times 1, 0, 0 plus v times 0, 1, 0 minus tk, or that the x component of ax is equal to u minus kxt, ay equals v minus kyt, and az is equal to minus kzt. And then, of course, we can rearrange to get t. So we get t is equal to simply az divided by minus kz. And then we can substitute that value of t back into the line equation to get the location of the intersection. Okay, and because we're defining all of our objects in their own local coordinate system, this is the only case that we actually need to consider for planes, because simply we can assume that all planes are defined as horizontal planes at the origin, and then we rotate them, translate them, scale them as necessary. Okay, so jump back to the episode about local coordinate systems, about geometric transforms, if you want to know more about that, if you haven't seen it already. Okay, so boxes. Let's have a look at how we could actually think about implementing a box. Now, of course, we could construct a box quite simply using 6 separate plane objects arranged to give all of the faces of the box. We've already implemented finite planes in our ray tracer, so we could really do that. But this would be quite inefficient and fairly inflexible. Okay, so it turns out that there is actually a better way to do it by defining each face as a plane belonging to the same object. And this is easy to do because we only need to consider the local coordinate system for the box, where it will always be a unit cube located at the origin. Okay, so this is the geometry that we're considering. This is a unit cube located at the origin, and I've shown this just to show how I've numbered the faces. Okay, so face number 0 is the lowest horizontal face. Face number 1 is the top face, so 0 is the bottom face essentially, 1 is the top face, 2 is the left face, 3 is the right face, 4 is the front face, and 5 is the back face. I hope that's clear. Wasn't quite sure really where to put the 5, but I think you'll see what I mean from that diagram. Okay, so that's important. So what we get, if we consider each of those planes, as I've shown in this table, plane 0, 1, 2, 3, 4, and 5, we can define a specific value for the point P0, as well as the vector P01 and the vector P02. And these turn out to be something like this. So point 0 is going to be 0, 0, 1. Okay, so that is a point on the plane. So the origin is in the center here, and then 0, 0, 1 represents a point on this plane down here, because remember, in the coordinate system that we're using, positive z is down. Okay. So, and then a vector from 0 to 1 is simply 1, 0, 0, so that is a positive vector in the x-axis, that would be that way, and this way 0, 1, 0, positive vector in the y-axis, which would be that way. So that defines that plane, and so on. You can go through the rest of these and you can see how they work. These are the values of P0, P01, and P02 for all of the 5 planes. Okay. Notice the change of sign here is this is positive 1, negative 1, but then the others are negative 1, positive 1, negative 1, positive 1, and that is because the z-axis in my coordinate system is essentially reversed, with positive z being down. Okay. So, as I've just said, for plane 0, we would have that A is equal to 0, 0, 1 plus U times 1, 0, 0 plus V times 0, 1, 0 minus TK, or that AX is equal to the X component of A, AX is equal to U minus KXT, AY is equal to V minus KYT, and now AZ is 1 minus KZT. So we can rearrange that to give that T for plane 0, which I've called T0, is equal to AZ minus 1 over minus KZ. Pretty straightforward. And we can do the same for plane 1. Remember, plane 1 was the top plane, so now we have 0, 0 minus 1 for P0, but P01 and P02 are the same, and we end up with AZ is equal to minus 1 minus KZT, which we can rearrange to give that T1 is equal to AZ plus 1 divided by minus KZ. And we can repeat that for all of the planes to actually give this. So we get T0 and T1 that we've just seen. We get T2, which of course is the left plane is AX plus 1 divided by minus KX, and T3 is AX minus 1 divided by minus KX. And then T4 and T5 are the front and back planes respectively, which give AY plus 1 divided by minus KY, and AY minus 1 divided by minus KY. And that gives us a value of T for every possible intersection between the ray and the cube. Now all we have to do is decide which one of these was closest to the camera. Okay, and we can also compute U and V for each face, and I've simply shown these here in this table. So U and V shown for each of the 6 planes. So yeah, U for plane 0, we have that U is equal to AX plus KXT, and V is equal to AY plus KYT, and so on. You can see for the rest of those. And in fact, actually to evaluate all of those, we only need to work out, or to compute AX plus KXT, AY plus KYT, and AZ minus KZT. And then we can use those to calculate all of the values for U and V. Now, because we're defining these as being all located a unit cube at the origin, we know that we will be inside the face if the absolute value of both U and the absolute value of V are less than or equal to 1. So that gives us a very straightforward way to test. So we can test for intersections, we can compute the values of T, we can decide which face, if we had any intersections, we can decide which one is closest to the camera, and then we can compute U and V, and we can compute whether we were inside the face or not. And that is actually everything that we need to do to implement boxes. The geometric transforms that we talked about in that episode then take care of transforming our unit cube from the origin to wherever we want it to be in our scene, and we can scale it to make it into any whatever box shape that we want. Okay, so that's pretty straightforward. Let's jump in and have a look at how I went about implementing this in C++. Okay, so just at my terminal window, if we go into the QB ray trace folder, this is as we've seen, and we put all our shapes into QB primitives. And before someone points out, yes, I know I spelled primitives wrong, but what I've done is defined here box.cpp and box.hpp. Alongside, we already have cone, cylinder, base class, of course, plane and spheres. So let's have a look. Let's just go back and let's have a look at how I went about implementing that. Let's look at box.hpp first. Okay, so this is box.hpp, simple class definition. It inherits from object-base.hpp that we talked about before. And we simply have the classic include guards for everything as we do. We hash include object-base.hpp and we bring in gtfm.hpp, which we're using to define our geometric transforms. And we put everything into the qbrt namespace, and this is simply class box that inherits from object-base. So the default constructor simply defines the unit sphere at the origin, simply called box. We override the destructor from the base class, so we have virtual tilde box override, and then we simply override our function to test for intersections. That's a standard format, we've talked about that before, and we declare 3 private variables for t, u and v, and note that these are declared as std arrays with 6 elements. Okay, 6 elements because we have obviously 6 planes, they're a type double, and we want to compute t, u and v for every plane. Okay, so we're using an std array object to achieve that. Okay, and that's everything we need for the header file. It's pretty straightforward. Let's jump in and have a look at the CPP file. Okay, so here we go. This is box.cpp. Of course, we hash include box.hpp. I've hash included this file here, qbutils. That's just for debug. Don't need to worry about that. It just gives me an easy way to print vectors. Hash includes cmath as well for math. So we have our constructor and destructor. They don't need to do anything. The only really interesting function that we have is the function for test for intersections, which is here. Okay, the first thing that we do is we test the visible flag. So if the object is visible, this is simply a flag in the base class that we can use to turn an object on or off in the scene. If that's not true, then we simply return false, so we have no intersections. Then we copy the ray and we apply the backwards transform to it. So we're making this new ray called BCK ray. We simply use M transform matrix. This is from the base class, okay, and we apply that in the backwards direction to cast ray that comes from here, okay. We extract the values of A and the values of K like that. So those are from the equation for the line that we saw just now. So we get AX, AY, AZ, and we get KX, KY, and KZ, okay. We normalize K first, okay. So notice those are the start and a point on the line and a vector representing its direction from the ray, okay, after the transform. And now what we're going to do is test for intersections with each plane or each side of the box. And first of all, we consider the top and the bottom. And first of all, it's important to check if we might be parallel or very close to parallel to the top and bottom faces. And we can do that simply by using if we're not close enough, if kz is not close enough to 0. So if kz is 0 or very close to 0, then we know that we must be parallel to the top and the bottom faces, in which case it would make no sense to try to test for intersections. Close enough, of course, being a function from the base class that simply evaluates if we're within a specified tolerance of 0. We don't use an actual test for equality because we're using double precision. We could end up being extremely close to 0 but not equal to it, which would still yield potentially erroneous results when we went on to do these calculations. So we use the close enough function to do that instead. And assuming we pass that test, so we're not close enough to parallel, we then calculate T0 and T1 for plane 0 and plane 1, simply using AZ minus 1 divided by minus KZ and AZ plus 1 divided by minus KZ, as we've already seen. And then we calculate U and V also for plane 0 and for plane 1 from the values of T as we saw. If we do not pass this test, so if we are parallel, then we set T0 and T1 to some arbitrarily large number, and we set U and V for plane 0 and plane 1 to 0. We then repeat exactly the same thing for the left and right faces, so this is now testing Kx is close to 0, and we're doing T2 and T3, and U2 and U3, of course, exactly the same. And then finally we have front and back, where we test Ky is close enough to 0 or not, And we do T4 and T5 and U4 and U5 exactly the same way. Okay, so that's really straightforward. That is our basic test, and it gives us our values of T and U and V for every face of the cube. Okay, and then we simply want to find the index of the smallest non-negative value of T. So we're going to create three new variables: final U, final V, and final T. These will be the final results that we want for whichever face that we've decided we've intersected with. We declare an integer or final index, which we set to 0, and we set a flag here, Boolean flag called valid intersection there to false. And we're going to loop over every face, so I equals 0 to I less than 6. Okay, and then we simply test if T of I is less than final T. So we set final T to an arbitrarily large number to begin with. So this is a classic algorithm to find an element is smaller and, identify the smallest element in the array. And yes, I know there are ways you could do that from the STD algorithm library, but I've chosen to do it this way. I often think it's easier just to bash out my code, particularly because I wanted to combine it with other tests. Anyway, so if Ti is less than final T and Ti is greater than 0, okay, so we want the smallest non-negative value of T. A negative value of T would mean our intersection occurred behind the camera or behind wherever the ray originated from. And then we combine into that a test that abs U of I is less than or equal to 1 and abs V of I is also less than or equal to 1. So if any of these is not true, then we don't have a valid intersection and there's just no point doing anything else. Okay, so if T is too big, then we don't worry about it because we only want the value of T that corresponds to the plane closest to the camera. If T is negative, we ignore it, and if abs U and abs V, or if either of abs U or abs V is greater than 1, then we know we're not within the face, so we just ignore it. Otherwise, we store final T, final index, final U, and final V, just like that, and we set valid intersection to true. And then after that, if valid intersection was set to true, we now are going to actually compute the point of intersection. Okay, so we compute the POI is simply, we take the final value of T, and we multiply it by K, and we then have BCK ray like that. So that gives us the point of intersection. That is just the equation for the line. Okay, a point plus T multiplied by the vector K. And remember the vector K came from here. It is the direction of this ray here. Okay. Now that is the point of intersection in the local coordinate system. That's very important to understand, to remember. We're then going to compute the normal vector. In fact, we don't compute it, they're just defined. We set up a blank vector there for normal vector, and then we simply have this case statement that switches over final index. If it's 0, 1, 2, 3, 4, or 5, we know which face that we're considering, and then we can simply define the normal vector easily enough. So in the case of 0, we know the normal vector points downwards, so it's positive z. In the case of 1, it points upwards, so it's negative z, and so on. Okay? That's pretty straightforward. And then we simply transform the intersection point back into world coordinates, okay, using int point is equal to m transform matrix dot apply POI, which is the point of intersection in the local coordinate system, and QBRT : forward T form, okay? And then we transform the normal vector using the apply norm function from m transform matrix. So local norm is m transform matrix dot apply norm to normal vector. And I did an episode looking at fixing the normals where I talked about that. Link in the description below if you want to know more. We normalize that and simply return it. Local color is m base color, and MUV chords set element U to final U, and MUV chords set element 1 to final V. And then we return true, because in that case we had a valid intersection. Otherwise we return false. And that's the end of it. It's really quite simple. And I think this code is relatively efficient. I will be the first to admit that it's possible that this could be optimized further. But I found this to be, I think, is quite a good combination between readable code and efficiency, and code that I think relates easily to the maths that we've looked at in the slides before, which I think is quite important. Okay, so let's have a look. I've gone and modified the scene class to create a simple demonstration of this to show that it works. So let's just have a look at that now. Okay, so this is in scene.cpp, which we've talked about many times, so I'm not going to go over it in great detail. and we include the box class in the HPP file, so we don't have that here. So we set up our camera as before, we set up the ambient lighting, we've talked about that, we create some textures, the image texture and the checkered floor. We set those up, as we've talked about before, create some materials, more here than I need. I've been doing all sorts of testing. We set up the materials, we've seen that many times. And then we create and set up the objects, the floor, the image plane, the three spheres, and here is the box. So all we do to define a box is simply auto box is equal to std : make shared to make a shared pointer to our box object of type qbrt : box, and we call the qbrt : box constructor function. Doesn't actually do anything, but that doesn't matter. And then we set the transform matrix for box using qbrt : gt form. We set this as the translation, this is a rotation, so we set those no translation, no rotation, and the scaling, just to show that you don't have to make a cube, I set that to a half on the x-axis, 2 on the y-axis, and 1 on the z-axis. And then we assign a material, and I've assigned the material I called cone material, which is simply here. So that's going to give us yellow-ish with a reflectivity of 0.15 and a shininess of 32. And then, of course, we just push everything back into an object list, and that's pretty much everything that we need to do. Okay, so let's compile our code, and let's have a look at the result. Back to my terminal window, just going to run make to compile everything. You know, if you're not familiar with the make files and everything else it's talked about, I think I covered that in the first episode of this series, so you can go back and have a look at that. Okay, that's compiled everything properly. If we run /QBRay, we should get our result, and you see it's reasonably fast. I mean, this isn't a very complicated scene, so yeah, it's not too bad, but we can probably work on performance. We'll look at that in a later episode. Anyway, and there we go. That is the result that we get. So we have a yellow, shiny box. It's not a cube because we scaled it. We scaled it to a half on the x-axis and 2 on the y-axis and 1 on the z-axis. So that's what we've got. And there we go. We see very clearly we have successfully implemented boxes. Okay, and that's it. That's really everything that I wanted to talk about today. So that is all of the code we need to implement boxes. Now, boxes are actually a lot more useful than you might think. So first of all, obviously it's nice to have a box primitive that we can use to create boxes in our scenes, but actually they have a much greater application than that. And the most important case really for me where we can use boxes is to use them as bounding boxes. Now, we haven't needed bounding boxes so far, but in later episodes when we come to look at creating more complicated shapes and more complicated geometry, more complicated maths to use to be able to compute the points of intersection, we don't want to have to be doing that for every pixel in our image. So every ray that we cast into our scene, some rays we know are going to go nowhere near that object and they're never going to interact with it, and so there's no point evaluating the maths for that object, for that ray, when clearly there's no intersection. Now the easy way to solve that is to put the complicated object into a bounding box, and then simply when you test the first intersection, you test for the intersection between the ray and the bounding box, and only if you have an intersection between the ray and the bounding box do you then go on to test for intersections with the more complicated object. Anyway, that is something we will talk about more in a later episode, but it is, to my mind, really the principal application of box shapes is bounding boxes. And as I said, of course, it's important to have a box primitive to construct things in our scene. So limitations to what we've done here, the UV mapping is very primitive. So at the moment, the whole UV space is mapped onto every face of the cube, which is clearly not really what you want. So if you were to map an image onto this box, it would then simply render the whole image onto every face. Now that isn't ideal. Normally for a cube or a box, you would unwrap the cube into a flat surface so that every face then has its own unique portion of the entire UV coordinate system of the UV space. That is something that perhaps I will look at in a later episode, but for now I just felt that was a little bit of a step too far, and I think, you know, I've shown the basics really of how to do boxes, and to be honest, mapping the UV coordinates onto different geometry is really not that difficult anyway. Anyway, there we go. As I said, that's really everything I wanted to talk about today. I really hope that's been an interesting video. I really hope you've enjoyed watching it. It's been a great deal of pleasure making it, so thank you very much for watching. And yeah, so a new video will be coming soon-ish. I'm not going to make a promise as to when, but we're going to start looking at more complicated shapes, more complex geometry, and in particular I want to go on to look at comparing ray tracing to ray marching, and then talk a bit about conditions where we can use both of those different approaches. Anyway, there we go. I think that's more than enough for today. So listen, thank you very much for watching. It's been a pleasure. I really hope you've enjoyed it, and I really look forward to seeing you in the next video. Bye.